on this computer. All right. We are now recording. Woo. All right. So how's everybody doing?
Good.
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 A little bit overwhelmed.
A little
if I'm
bit
being
overwhelmed.
honest.
Biochem can be overwhelming. That's why I like it. And so, all right. So I think what we'll do, because I only know maybe one or two people. Well, three, because there's two in one screen. I think what we'll do is maybe just introduce ourselves, because this will probably be the crew that'll probably be there for the other study sessions as well. And if we have anybody else who joins, that'll be good. And so I'll just say my name real quick, and then if you guys just want to introduce yourselves and maybe state your major. All right. So I'm Dr. Bishop. I was a full-time professor of biochemistry there, and then I'm actually in my office at the church now, and so I've been there for a little over a year. But I still teach occasionally on an adjunct basis, and so that's a little bit about me. We'll start up with Morgan. We'll go around that way.
Okay. Hi, I'm Morgan. I am a chemistry major, and were we supposed to say anything else?
Nope, that's me.
Okay, there you go.
And I'm Isosa, and I'm a biochemistry major.
Oh, am I next?
Sure.
Oh, well, I'm Will, and I'm a biology major with a chemistry minor.
I'm Alex. I'm a biology major.
Okay.
I'm Josh. I'm a biology major.
Okay.
I'm Jordan, and I'm a pre-med biology major.
I'm Alicia. I'm a biology pre-med major.
Okay.
I'm Abigail. I'm a biology major as well.
Okay, perfect. All right, so you guys have been in class this is your second week, right?
4 weeks.
4 weeks. Oh, wow. Yeah, that's right. 4 weeks. Huh. Time flies in 2020. So you guys should be coming up on your first exam soon, right?
Mm-hmm. Next week.
Next week. What day?
Wednesday,
Friday.
Friday.
Wednesday to Friday. The day is yet to be specifically determined.
Okay. So if you guys need, so we'll talk a little bit today, but if you guys want to have another review session before if the exam gets scheduled for Wednesday and you want to do another review session before then, just let me know, and I'll try to work something out, just in case it gets scheduled for Wednesday. Okay. So then let me just remember, because it's been a while. So you guys talked about weak acids and weak bases.
Yeah.
Okay. And you guys talked about amino acids.
That's basically where we're rounding up now.
Okay. Have you started protein structure yet? No.
No, that's exactly what we've started on Monday. Or not Monday. Yeah, Monday.
Protein structure, amino acids. Oh, protein
structure.
purification. Okay. Oh, yeah, good stuff. Oh, that's a lot of good stuff. All right. So then I'll just open it up to you guys, at least to start off with, just to see what we need to go over. If you guys have any questions about anything or everything.
Okay.
Can we start off on the Henderson-Hasselbalch equation?
Oh, Henderson-Hasselbalch. Yeah, Henderson-Hasselbalch. Hey, you guys are going to have to help me out with this because, like I said, I don't have my notes. Henderson-Hasselbalch equation is for buffering systems, right? Because buffers are very important. Oh, this is where I'm going to get it mixed up. This is why I need you guys to help. But you probably can't see this, but Henderson-Hasselbalch is very important for buffers, right? I believe it was pH is equal to pKa plus the log of the conjugate base over the acid.
Yes.
Sweet. All right, Dr. Bishop for the win. Right, and so this was for base systems, right, or buffering systems, right? And buffering systems are very, very important in biochemistry, right? Because we are one huge buffer, if you want to think of us that way. And so was there a specific question about the Henderson-Hasselbalch equation that you had?
Not really, but
huh?
not really, but it's just what confuses me is like calculating the concentration of the base and acid.
So calculating the concentration of base and acid when you're given a pH, or when you add acid or base to a buffering system, because there's two different types of questions there.
Both are
Like,
confusing.
Both.
Yeah, when we went over it in class, she kind of just went for it and then didn't slow down and wasn't very helpful with answering questions.
Okay. Do you remember the question that she did in class?
I have it written down.
Because in that way I can go through that one without having to make up one on the fly.
Yeah. Let me see.
we have our homework yet.
There was one question that I saw on the homework
Uh-huh.
where I was having trouble like even starting, like how would I set it up?
Oh,
I don't
yeah,
know if
I
you
like
can.
that one. Oh, I don't have mine. Okay.
It's number 2. A solution of acidic acid, pKa, is 4.76, is prepared with a concentration of 0.1 molars. The pH of the resulting solution is 5. Calculate the resulting pH values when you add 0.01 molars and 0.05 molars HCl and NH.
So 0.01 and 0.5. All right, so I'll just tell you right now, the 0.05. Yeah, okay. I was gonna say I thought I took off the 0.5. So, okay, so there's a couple things that we need to figure out. So we have this buffering system, right? This acetic acid buffer. We're given the pKa, we're given the starting pH, and we're given a starting concentration. So just to show you guys, so what do we know about 0.1 molar acetic acid? What has to be true about that?
There's 0.5 moles of HCl.
Oh, that's what we're going to be adding to it. I'm saying, so you make your buffer. First off, let's say, what are the two components of a buffer? Let's start there.
A weak acid
and its conjugate base.
Right, a weak acid and its conjugate base. So we're going to make a buffer that's 0.1 molar. Let's do some easy math and say we make a liter of it. So there's 0.1 moles, right? So again, if you're not given a volume, you always assume the volume. That makes the math really easy. And so there's no volume given. So we're going to assume 1 liter, which is which would cause the molarity to be directly converted into moles, which would be 0.1 moles. So we know there's 0.1 moles of what in our solution?
Acid.
And?
Base.
Base, right? Because remember, it's a buffer. And so we can't have more base. So the amount of acid and base cannot be more than the total amount that we have.
So there's a total of 0.1 moles, or each of them has 0.1 moles?
A total.
Okay.
Right? So remember, you're making a solution of 0.1 molar. And so we do the calculation, 0.1 molar times 1 liter, 0.1 moles. That's the upper limit. We have to have 0.1 moles. We can't have more and we can't have less. Thank you, conservation of matter. Right? So that's one of the things that we know. Okay? Using the Henderson-Hasselbalch, what else can we calculate based with the information that we have a pKa and a pH.
The ratio?
The ratio, absolutely. So let's go ahead and calculate the ratio. So we're going to have pH is 5.0, 4.76 plus the log A minus HA. Oh, math in my head. 5 minus 4.76. So this is, so I'm going to show you guys what I'm doing here, right? So then what we can do is we can solve for the log of the ratio. Can everybody kind of see that?
Mm-hmm.
Right? So then how do you solve for a log?
Use the anti-log.
That's right. Right, so if we were to do 10 to the 0.24, A minus HA, what we're going to get, I'm going to draw it over here. And I might have you guys check my answer because Mike, I'm using my phone calculator, right? So you take 10 to the 0.24, and this is what I get, is the ratio is equal to 1.7.
Is it to 10 to the 0.24 or to 10 to the negative 0.24?
Negative
2.24.
0.24.
Is it negative? Is it supposed to be negative? I don't know. I'm just asking.
Oops, that's not what I want. Let me check.
I don't think it's supposed to be negative because
No.
Okay.
Right, to
Yeah,
turn
I got
something into a P, you take the negative log of it.
Okay.
Yep, that's where the negative is. Huh. All right, so now let's think about this for a minute. Does that number make sense?
what does that number mean?
What do you think that number means?
That's the KEQ?
No, no.
That's
No.
the
Really?
ratio.
What does that number mean?
There's more acid than, no, there's more base than acid.
Yes. 5. Okay. Can somebody check? I think I have this switched. Let me do a quick search real quick. So I think I have the Henderson-Hasselbalch equation backwards.
You wrote it like I have it from your video.
Did I?
Mm-hmm. The A over HA.
Yeah. It's A over HA.
Plus log. Yeah, it is. All right. So I think, because that's not, so let's look at this, right? So right now we have the ratio is equal to 1.7, and we said that there's more base than acid. Would that make sense based on given the pKa and the pH of our solution?
Yes.
Yes.
Why?
Because the pH is greater than the pKa, and so that means that it will not be protonated. And, or there would be more of the conjugate base than there would be of the acid.
So then what should the pH be then?
For there to be more acid?
For there to be more base, right? Because based on our calculations, no, that's right. Nope, we're gonna do it. This is right.
Okay.
Just, I told you guys, I don't have my notes. So what I'll probably do then, well, my video has the problem worked through like this. I'll go back and look at my notes too to double check. If there's something I need to change, I'll change it and let you guys know. Okay, so what do we have up here? Here.
the 0.1
The
moles.
concentration.
Yeah. Equals the concentration of acid plus
But it's what type of, how many variables are in this equation?
2.
Right? What do we need to solve an equation with 2 variables?
At least the
Another
value of
equation.
Another equation. What do you think we have down here?
Another
equation.
Yeah. So let's go ahead and solve it for A minus,
one.
right? Because that makes the math easier.
1.7 HA equals.
Right? So what do you think we could do with the information we found down here?
Plug it in.
Up here. Yep. Just like the Glade commercials. Plug it in, plug it in. And then what can you do with 2 variables that are the same?
You can add them.
You can add them.
That would be 2.7.
So, like I said, with regards to the numbers, I am just a little bit unsure. So just, I mean, but the way that the way that we're solving this is exactly how you would solve those equations. All right. So now we can just divide by 2.7. And what do you think we end up with?
0.037.
But what is that?
Is it the moles of HA?
That's the
Yeah.
concentration.
It's the moles of HA.
Okay.
Or the concentration. I usually just put things in moles.
We like moles.
All right. Right, so now we know the moles of HA. How do we calculate the moles of A minus?
Subtract.
We plug it back up in here. Yep. So I will tell you this right now. This equation, it's very, very boring, to say the least. Okay. But if you're ever given an equation like this, these are the exact steps. So now, yay. So we now have the moles of A minus and the moles of HA.
Da, da, da.
Is there any questions on this?
Mm-mm.
I will tell you this is the first step of a multi-step process. Yay.
Yeah.
So then it's asking calculate the resulting pH values
Yes.
when you add 0.01 molar HCl to the pH 5 buffer.
Yep. So we have our buffer. Oh, that's right. Because the pH, sorry, you're right, Isosa. It's pH of 5 with a pKa of 4.76. So there would be more base than, I got that backwards. Okay. So, let's see here. So let's think of a chemical equation we can use, right? Because remember, what does a buffer system do? Why do we have buffer systems?
It equilibrates.
Right?
Yeah.
So we can depict what our buffer is doing with this equation, right?
Yes.
Can everybody see that? And does that make sense?
Yes.
Okay, right? Because that's what a buffer does, is it takes acid, makes conjugate, or takes protons and makes conjugate acid. All right, so we can do what I like to call Dr. Bishop's ice table. Yeah, because it's not a real ice table, but it's an accounting table. So we just calculated the initial amount
No.
of A minus.
Should be this way.
And we'll do you said 0.01 molar, correct?
Yeah. HCl.
Yep. So initially, what we calculated, I don't know if you guys can see that. right? We calculated that there's 0.063 moles of A minus and there's 0.037 moles of HA.
Where
Right?
did
That's
the
what we've already done.
2.7 come from?
Huh?
The 2.7?
The 3.7?
No, so above like
Oh,
when we
6.7. Whoa, wait. There. Sorry. Where did what come from? Sorry.
from right above when we were solving for the HA,
Uh-huh.
we went from like the 0.1 equals 2.7.
Ah,
Oh,
yeah.
2.
So the 2.7 was just because from our ratio, we found that for every one A minus, we had 1.7 H, right? So let's back up. Going the wrong way. Okay. Right, so we solved, where are we? Here. Right, from our Henderson-Hasselbalch equation, we found
Yeah.
the ratio of A minus to HA equals 1.7. So that was when we took the anti-log of 0.24.
Right.
Right?
Yes.
So then what we did was we multiplied HA. Yeah. So we got A minus is equal to 1.7 HA. We can then plug this into this equation for A minus.
Right.
And so we have 1.7 HA plus 1 HA. We add those two together and we get 2.7 HA.
Just the average. Just the average.
Okay.
Okay.
That's where, because you wouldn't just do 1.7 like times 2 and get.
No. No. Because we would just add it to whatever was in front of here, which is 1.
Okay.
And so it was 2.7.
Okay.
Right? And then we divide 0.1 by 2.7 and we get this.
Okay, I got it now.
And then we just plug that in and get this. So we have the initial amount, right? 0.063, 0.037. How much did we add to our solution? 0.01 molar, right?
Mm-hmm.
Of hydrochloric acid. So again, I'm going to assume we're going to add a liter of it. So we have 0.01 moles. Makes the math easier. So on this side, what are we doing with the conjugate base?
It's decreasing in concentration.
Right? Because we're using it up with these protons and we're making the conjugate acid.
Yes.
So what we do is we subtract from the reactant side and we add to the product side. So it'll look something like that. So it'll be 0.063 minus 0.01, right? Because we're changing it over. And then, but we're going to add to the conjugate acid, and we're going to make 0.047. Does everybody see how we do that?
Yes.
Perfect. So then how do you solve the pH change?
Henderson-Hasselbalch.
You got it. You just plug in the ratio, and then you can solve for the pH. What do you predict will happen to the pH?
It will decrease.
Right? It'll go closer towards the pKa.
Mm-hmm.
Because we're adding acid. Right? And those are just some things that we should think about as we're solving these problems. Because, let's see here, 4.81. So I get the pH of about 4.81. Thereabouts. Close enough. Right? And so like we said, so some of the things that we need to think about, right? Because obviously this is a math problem with numbers and stuff, but it's really a conceptual problem. And so if we just understand the concept of what the Henderson-Hasselbalch equation shows us and why we use it and how buffers work, it'll actually help us do the math a little bit easier. Does that answer some of the questions?
Yes.
Yes.
So you got a pH of 4.8?
Thereabouts. 4.81.
Okay. That's what I got. Dr. Bishop, did you ever do the neurotransmitter binding case study with your students?
Which one was that?
I have no idea. It's
Remind
this
me.
one. It I don't even know if you're gonna be able to see this. It has like, can you even see that?
Yeah, I can see some of it. I don't know if I did that one or not. How cool
Okay.
is that?
Oh, well, if you think it's cool, do you think you could help us?
It depends. I won't give you guys any of the answers if that's what you're asking.
Well, no, I think
No, I'm
like
just
right
kidding.
now at this point, I'm just confused on how to even start.
Okay, what's the question?
Do you want me to email it to you?
Yes, please.
Okay, let me get it.
Because then I can look at it. All right.
So while we wait on that, so when we calculated this new pH of 4.81,
Uh-huh.
that's when we added 0.1 moles of HCl.
That's correct.
And so to do the second part of the question, we would do the exact same process, but 0.1 moles of NaOH.
Oh, it asked for a base too.
So that's a good question. If it asks for a base, what do we have the most of the numbers, right? Because your starting concentrations are going to be the same. What do we need to change if we add a base?
We're gonna have less acid and more base.
Right. So how do we depict less acid and more base?
Would you subtract from HA and add to A minus?
You would just switch around. So this equation here, you would just do HA plus OH minus goes to A minus.
Okay.
Right. So again,
Yeah.
what like I said, this is a math problem, and it is, as you can tell, all the numbers. But this is a very conceptual problem. And what I mean by conceptual is that some of the things that, right, like that, oh, okay, so I know how a buffer works. OH minus is going to take the proton away from an acid and make its conjugate base. Okay, so then I need to switch around my equation using the numbers that we've already, right? So you don't have to do any other calculations at the beginning because that's already done. We're just now going to manipulate the system a little bit. There's a weird glare from my light I am now noticing. Oh, well.
So then we would get 0.073 for A and 0.027.
Yep.
And then go from there.
That's right. And then Henderson Hasselbalch.
Okay.
And then we'd get the pH, which should be a little over the pKa.
It would be a lot. It would be higher than what it is now.
Yeah.
Right. Because again, you're pulling more of that. You're pulling more acid away, and so it'd become more basic. That is correct. There it is. All right. Oh, I gotta do that too. Oh man, forgot about that. All right. Ooh, no, I did not do this one. All right. Binding forces questions in your graph to make sure that structure. Okay, determine which of the forces or bonds the symbol can be used to bind or stick to another molecule. Oh, okay. Yeah. So the first question is just so here's serotonin. What just by looking at the structure, right?
Mm-hmm.
What kind of forces could you imagine being used? Which forces or bonds listed below can be used to bind the serotonin molecule to a protein or to another molecule. And then briefly, so a London dispersion force.
Mm-hmm.
Do you remember what a London dispersion force is?
Yeah, that's between the the non-polar.
Do you think there's something in this molecule that could bond through a London dispersion force?
Yes.
Not any of the side chains.
Correct, but there's more than just the side chains.
So then would it be like the benzene ring?
You got it.
Okay.
Right? Because it's a very, it's a very good molecule to bind, right? And so that's just what it's asking. And so, but see, yeah, I would say that's more of a London dispersion force than a hydrophobic interaction, but just because of, when you go through nucleic acids, you'll find that they actually use their benzene rings to interact with each other on the top and the bottom. But yeah, so that's what it's asking. So you just have to go through each one of those types of interactions, and you need to just say, okay, this is this type of interaction. Okay, yes, this can do it, and here's why I believe that.
Okay.
So
like, for example, there probably wouldn't be dipole-dipole forces because there's no side chains of CH.
That's right. That's what I would say.
Wait, there's no dipole-dipole?
Dipole? Hold on, let me look.
Yeah, I put the OH in the NH.
But the OH is attached to the benzene ring.
Yeah, I would say probably not a dipole. Right, because it's attached to the, there might be a dipole on that amide group or amine group that's at the top, right? That you can imagine with that those two methyl groups.
Yeah.
See that kind of fishtail. So that might be one, just because of the electrons being pulled by that nitrogen. But that would be the only one that I possibly might see on that one.
Okay.
So that's that one. All right, let's look through. Okay, pull up another paper. Okay. How many hydrogen atoms in the serotonin molecule can be donated to make hydrogen bonds? Okay. So that one's pretty straightforward. Which hydrogen bonds can accept from other molecules? Okay. So that's just, so you guys are familiar with hydrogen atoms making hydrogen bonds?
Right.
Maybe, right?
Vaguely.
Commonly found on what molecule?
Water.
Water, oxygen, right? I would check on the benzenes. I don't think they can hydrogen bond. And I would double check on the nitrogens because I think they can hydrogen bond. And so hydrogens can accept from other molecules, can be donated. Make hydrogen use.
Would it be that nitrogen on the 5 carbon ring? Or I guess it's not 5 carbons, but the...
Yeah. The one, see, that's just a weird wording of the question. Right, I know the donating one. So it's which ones form hydrogen bonds, but then which ones can accept from other molecules? That one's a little confusing to me.
Can we look at the lone pairs to
Yes.
whether they can accept it?
Yes, that's probably what that means. That nitrogen though, because that hydrogen. Because it's very this serotonin is very similar to a nucleic acid, and that nitrogen that's usually on the purine ring, pyrimidine, whatever. Usually donates that hydrogen to form a hydrogen bond. I don't think that nitrogen can accept a hydrogen bond, but I could be wrong. Okay, so part D, determine which intermolecular force would provide the best interaction with the serotonin molecule at the specific point labeled A, B, and C. Okay. Some bonds are free to rotate. Would this conformer of certain by tightly, less tightly, about the same? Okay, an increase in pH would change it. Oh, okay, I like that one. Yeah, I like those questions. So really what you're doing is you're going to think about which type of interaction, right, that C could form, that B could form, and that A could form. And you're just going to, in order of strength, have you guys talked about order of strength with regards to interactions, right?
Yeah.
Based on the order of strength, which one would be stronger? Which one would be intermediate, and which one would be weakest? And then what you're going to do for E, F, and G is you're going to use your rankings and then determine how things would change if you were to change the pH in F, if you were to change the stereo, if you were to change the conformation in E, and then if you were to flip it in G, would you be able to get the same binding as you did previously? And then let's see here. Briefly explain why it will either bind as tightly, much less tightly, or much more tightly. I don't think anything will bind much more tightly, to be honest with you. And so there's that. Other metabolites moving around. Examine the possibility shown below in this molecule. Dopamine. Oh yeah, okay. And then you're just going to do it with different molecules. So you're going to say, okay, let's look at dopamine based on what we saw before with how serotonin interacts. How will dopamine now interact? How will glucose interact? And then how will tryptophan interact, which is the derivative, which actually starts the dopamine process, serotonin process. Can you suggest a means by which nature could allow the binding of serotonin to the receptor while preventing the binding? Oh, okay. Yeah. So does that help at least kind of guide thinking on these questions? Okay. I actually really I didn't assign this one, but I really like this one.
I'm glad that you like it.
I really like that one. I might actually no, I'm just kidding. I was going to say I might have to actually do it now, but yeah, that's not going to happen. All right. Let's see here. Do you guys have any other questions?
How would you best recommend, like, what things should we focus on for studying for this next test? Like,
Thank you. That's also what all of our professors have told us.
just study everything that I've ever taught you.
That's exactly, I mean, if it wasn't important, we wouldn't be teaching it to you guys. No, I mean, with biochemistry, it's really easy to get into the nitty gritty, right? Mm-hmm. As you can see by some of these things, right? Because there's just a ton of information. When I taught it, I was more worried about the concepts, right? So a lot of the stuff that's on this case study, I mean, that's very conceptual, right? Taking what we know, the information we know, and then kind of conceptualizing it. Okay, so I know this about ionic interactions. What does that really mean, right? So you know, I don't know, I think you guys talked about protein purification, right?
Yeah.
Protein purification takes a lot of those types of interactions and then utilizes them to purify the protein. And so that's where I would focus on. Did you guys did she give you guys a study guide?
She said she made one, but today when she was looking for it on Canvas, she couldn't find it. So she was like, well, it'll be here.
Okay, well, if it'll be there, I would just see I would focus on that. Okay. And so, yeah, that's what I would say.
And I think the exam is scheduled to be on the 25th, okay. So not next week. Well, or did she say?
Yeah, it's supposed to be next week.
Okay.
But it may or may not be pushed back, she said.
Okay. Well, just let me know if that gets pushed back. And if you guys have any other questions as you guys are studying, shoot me an email. And so that way then I can answer them in more real time, just so that you don't have to wait a week before we do this again. So do you guys have any other questions? I hate to cut this maybe a little bit shorter today, but I've got somewhere I got to be. So do you guys have any other questions? And if you do, like I said, just go and send me an email and then we'll go ahead and if if your test just happens to get scheduled, like it just happens to be before our next meeting, just let me know and we can work something out.
Okay. Yes, sir.
All right. So do you guys have?
Thank you so much for volunteering to do this.
No problem.
You're saving our GPA.
No, you guys are smart. You guys are smart. I trust you guys. Based on some of the answers you guys gave me through doing some of the work, I think you guys will be fine. It's just a lot real fast.
Yeah.
And I understand. All right. So I'm going to go ahead and stop recording this, and then we'll go ahead and end the meeting. And I will post it to the YouTube channel.